In the first part of our video on solar radiation, we discussed the basic properties of light, the electromagnetic wave spectrum, and the power emitted by our sun. We will now continue our discussion by looking at the spectral distribution of solar radiation. Not all wavelengths of our light are emitted equally by our sun. Moreover, solar cells can only use a fraction of the incident wavelengths. The spectral power emission, or spectral radiance, is defined as the radiated power per unit wavelength. A body with a temperature above absolute zero, which is 0 degrees Kelvin, emits electromagnetic radiation. The spectral radiance of such a body is described by Planck's law, which is shown here. Planck's law assumes that the body is a black body. A black body absorbs all the radiation that is incident on it. A perfect black body does not exist in nature, but planets and stars are close enough for Planck's law to give a very good approximation of the spectral radiance. The spectral radiance of a black body is a function of only its temperature T. It is remarkable to see that Planck's law contains three fundamental constants: Planck's constant, Boltzmann constant, and the speed of light in vacuo, which are among the most important constants in physics. This figure shows the spectral radiance of three different black bodies as a function of their wavelength. The bodies have a temperature of 6000, 5000, and 4000 degrees Kelvin respectively. We can see that the total emitted power increases strongly with increasing temperature. Furthermore, the peak of highest power density shifts toward the lower wavelength region with increasing temperature. The surface of the Sun has a temperature of roughly 6000 degrees Kelvin, so the spectral radiance of our Sun follows the yellow line. To calculate the radiance a black body with the size and position of the Sun would have on Earth, we have to multiply the spectral radiance with the solid angle of the Sun as seen from Earth. This is described by the shown equation where I is the irradiance and omega Sun is the solid Sun angle. The solid Sun angle is described by the following equation, where r Sun is the radius of the Sun, r Earth is the radius of the Earth, and AU is roughly the distance from Earth to the Sun, known as an astronomical unit. The solid Sun angle is therefore equal to about 68.5 microstar radian. The spectral irradiance by the Sun on Earth, as described by Planck's law, is shown in this figure. The dashed lines indicate the boundaries of the ultraviolet, the visible, and the infrared part of the spectrum. If we now introduce the empirical data of the spectral solar irradiance, we can see that Planck's law gives a very good approximation. Only in the visible part of the spectrum is the irradiance underestimated. The red curve shows the spectral irradiance outside of the Earth's atmosphere. This spectrum is known as the AM0 spectrum. If we look at the spectral irradiance on the surface of the Earth, we can see that the irradiance is significantly lower. The shown spectrum is known as the AM1.5 spectrum. It includes absorption of light by particles in the Earth's atmosphere. Let's look at this absorption in a bit more detail. A large fraction of the visible and ultraviolet light is absorbed, while in the infrared part of the spectrum the absorption is more concentrated. These absorption bands are caused by specific molecules in the Earth's atmosphere. Most bands are caused due to the light absorption by water molecules, but absorption is also caused by carbon dioxide, oxygen, and ozone. The absorption in the atmosphere causes the total irradiance to decrease from about 1360 watts per square meter in the AM0 spectrum to approximately 1000 watts per square meter in the AM1.5 spectrum. The latter is known as one-sun illumination. As we have just discussed, solar radiation passing through the Earth's atmosphere is attenuated. The most important parameter that determines the solar radiance under clear sky conditions is the distance that the sunlight has to travel through the atmosphere. This distance is shortest when the Sun is at the zenith, so directly overhead. The ratio of an actual path length of the sunlight to this minimal distance is known as the optical air mass. The figure shows the Sun at its zenith position. As it illuminates Earth, light travels through the four main layers of Earth's atmosphere, excluding the exosphere. These layers are the troposphere, stratosphere, mesosphere, and thermosphere. With the Sun at its zenith position, the optical air mass is unity, and the spectrum is called AM1. In space, no atmosphere is traversed, so the spectrum is known as AM0. When the Sun is at an angle theta with the zenith, the air mass is given by 1 over cosine theta. When the Sun is, for example, at an angle of 60 degrees with the zenith, we receive an AM2 spectrum. The AM1.5 spectrum we showed earlier is obtained for an angle of 48.2 degrees. How much power is actually incident on a specific surface varies with the time of day, with the seasons, and the position on Earth. This figure shows the average global horizontal irradiance, which is the power incident on a horizontal surface averaged over the entire year in kWh per square meter per day. While on average a solar panel in Northern Europe may only receive 3 kWh per square meter per day, around the equator this number can go up to 6 or 7. A more convenient way to express the irradiance per day are the daily equivalent sun hours, or ESH. An equivalent sun hour is defined as the number of hours one sun illumination per day. Since one sun illumination is equal to 1 kilowatt per square meter, one daily equivalent sun hour is equal to 1 kilowatt hour per square meter per day. If we look for instance at this map of the Netherlands, which shows the yearly sum of irradiation for panels with an optimal tilt angle, judging from the color distribution we can assume an average yearly irradiation of about 1250 kWh per square meter per year. Dividing this amount by the number of days in a year, we find that the Netherlands receive on average about 3.1 kWh per square meter per day, which means about 3.4 daily equivalent sun hours. In order to compare the performance of different types of solar cells in different locations, the solar cell temperature and irradiance have to be controlled. To that end, the standard test conditions are defined. These conditions are characterized by a total irradiance of 1000 watts per square meter, the AM1.5 spectrum, and a cell temperature of 25 degrees. To measure a solar cell on a controlled AM1.5 spectrum, solar simulators are used, like the one shown in this picture. A solar simulator uses a special lamp or set of lamps to mimic the AM1.5 spectrum as closely as possible. The spectral irradiance received from such a solar simulator is shown here. The blue area depicts the emitted irradiance, while the red area depicts the part of the spectrum used by an amorphous silicon solar cell. If we overlay the AM1.5 spectrum in the spectral range, we find that the solar simulator provides a very good approximation of the AM1.5 spectrum in the range used by the solar cell. Now, in summary, we described how sunlight can be described as a flow of photons or a wave. We saw how wavelength and frequency are important properties that define different ranges in the spectrum of electromagnetic radiation. We discussed Planck's law for blackbody radiation and compared it to the spectral radiance outside the atmosphere and on the surface of the Earth. We discussed the concept of air mass, and finally we defined the standard test conditions in solar simulators. In the next video we will discuss the photovoltaic effect.